So let's look at a matrix one where we have some specific stipulations on what our matrices will look like. We're going to let V be the set of all invertible 2 by 2 matrices. We're going to use standard addition and scalar multiplication for this. So we're not changing any definitions, but we're asking, does this produce a vector space? Take a minute, pause the video, think about whether or not you're going to get a vector space. Remember, to have a vector space, the two big things you have to check are closure under addition and scalar multiplication. So the question then becomes, if you were to add two vectors together in the space, do you necessarily get something that also lives in the space? Pause the video, think about it, then we'll come back together and talk about it. So let's look at a few examples here. Now, remember, to be invertible, and we're talking about 2 by 2 matrices. So 2 by 2 matrices look like this, right? So the definition of invertible, we can actually think about things in terms of the determinant. So as long as the determinant is not 0, then we're good to go. So let's come up with two matrices that live in this space. Well, 1, 2, 3, 4 live in this space, right? So if we were to look at the determinant here, the determinant of this matrix would be 4 minus 6, which is negative 2. So this is an invertible matrix. Now let's look at this one. Okay, now that would be the additive inverse of this matrix, right? Because if I were to add those together, I would get the 0 matrix. We're asking, is this invertible? Well, let's look at the determinant. So the determinant here would be 4 minus 6 also, which is negative 2. So this is invertible. So we have two matrices that are invertible. But check out what happens when we add them together. We're looking for closure under addition. So the question is, if I take any two matrices in here, do I get something else that's invertible? Well, if I add these together, I get the 0 matrix. And the determinant of the 0 matrix is 0, which means it is not invertible. So this guy is not closed under addition. So remember, it only takes one example to really kind of just mess everything up for you. In this example, we had two matrices, both were invertible. However, that sum is not invertible. So we're not closed under addition. In fact, this guy's not even closed under scalar multiplication. Remember, scalars can be anything. They're any real number. So what if we were to let the scalar be 0? Well, then 0 times any matrix is going to produce the 0 matrix, which has a determinant of 0, which is not invertible. So this set just has a whole bunch of problems, right? It's not closed under addition, it's not closed under scalar multiplication, and there's even going to be some other properties that just fall apart with those definitions. So this guy is not a vector space. And we only have to have one problem, one axiom that falls apart to show that it's not a vector space. You really only need one counterexample to show that something does not work. But to show something works, you have to show it for every example. And that's why we use all those variables to show it for every example. I encourage you to look at 35. You may want to pause the video, work through them, and then see what happens with these. A and B, we've already talked about. They're both in R2. Under A, we have standard addition, but multiplication was changed, where that scalar only goes to that first term, not the second term. And remember, we said that this was not a vector space. Number 8 fails. B, we've already done also. Actually, just kidding. B, we did not do. Now the addition axiom has changed. Scalar multiplication remains the same. So it's kind of the opposite of what we did in a previous video. So you may want to pause the video, determine whether or not this is going to be a vector space, figure out which axioms fail, and then come back and compare your answers. So if we look at 35b, notice we've changed that definition of addition. Scalar multiplication is going to be fine. So this guy actually turns out not to be a vector space. And there's several things that fail. Number 2 fails. So if I have 2 vectors in this space, I'm just going to use that x1, y1, x2, y2. So notice what that definition says. If I add this vector to this vector, that y is always going to be 0, and the x is always going to be whatever that first term was. So in other words, that order is going to be really important. So let's look at axiom 2 a little bit closer. If I take x1, y1 plus x2, y2, and I add those together, by that definition of addition, I'm going to get x1, 0. Now, axiom 2 is about the commutative property. So if I were to change that order of addition, now I'm going to get x2, 0. Because remember, it's going to be whatever that first component is. Think about, you really have to be careful with these definitions and what they're saying. Think about what this is saying. If I add 2 things together, I get the first component, and then I always get 0. So axiom 2 fails. 3 is actually okay. 1 is okay. It's still closed under addition, and we still get something in R2. Okay, let's look at number 4. So axiom 4 is about the 0 vector. So if I take any vector and I add the 0 vector to it, I get the vector x1, 0. And notice that's not the same thing as what we started with, right? So this one fails. In fact, number 5 fails also. So there's quite a few failures here. If we were to take x1, y1, and we were to add its inverse, and we would think the inverse would be negative x1, negative y1. It actually doesn't matter what that second component is, to be honest, because it always maps to 0. But if I were to add these together, I get just that first component, x1. And so that's not the 0 vector. And in fact, there's no way to get to a 0 vector. So axiom 5 fails. In fact, it also turns out the number 8 fails. if we take C plus D times this factor, then we're going to get C plus D times x1, and then we're going to get 0. I'm just kidding, sorry, we're under addition. So now we're using that multiplication rule. So standard multiplication. Standard rules now. But if we look at the other side, this would be C times x1, y1 plus D times x1, y1. We should get the same thing, right? If the axiom holds. So this guy would be Cx1, 0. This one would be Dx1, 0, which is Cx1 plus Dx1, and then we get 0. So they are not the same thing. So number 8 fails also. So this one just has a lot of problems. This is not a vector space. Okay, take a minute, look at C. You may want to pause the video and think about that. So C is just going to have a lot of issues also. This is not going to be a vector space. So just lots of different problems. Notice addition is standard addition. It's just a regular old way we would add vectors in 2 dimensions. However, this guy is extremely different. We're taking that scalar and we're putting it under a square root, which means there's going to be some problems. Remember, scalars can be anything. Positives, negatives, and 0. Well, positives and zeros aren't a problem. It's the negatives that are a problem. Because if we take the square root, let's say C is -1. If we take the square root of a negative, now we're not in R2. We are in the complex plane. So it's not an element of R2. All because of the way we've defined that scalar multiplication. So lots of issues here, right? This one's not a vector space. It turns out there's a few things that fail. I got that number 6 fails, number 8 fails, and number 9 fails. So just some lots of problems. And I'll let you think about those and work those out. In that last example, 2 failed, along with 4, 5, and 8. So lots of problems there also. So what I want to do now is I kind of want to have some fun with this. So let's look at this one. This is one of my favorite ones. So we're going to let V be the set of all positive row numbers with non-standard operations defined as. So we've got 2 vectors. If we add these 2 numbers together, it turns out it's really multiplication. And if we were to look at scalar multiples, k is a scalar here. So scalar k times u, which is a positive real number, then it turns out to be exponential. It's going to be u to the k. The question I'm asking, is this a vector space? Okay, so first let's understand what this world kind of looks like. Okay, so we really need to understand what does this look like in order to really do things with variables. I'm a firm believer in let's try it with numbers first and then let's throw some variables in. So let's say we take the numbers 1 plus 1. Those are two positive row numbers. Under this definition, if I were to add them together, I'm really going to end up multiplying. So I'm going to get 1. If I take 2 plus 3 here, I have positive row numbers. I'm adding them together under that definition. That means multiply. So we're going to get 6. Now let's look at that scalar multiplication definition. If I take 2 times 1, okay, notice the k is the first number. So this is going to be our u, which is 1 to the k. So I'm going to get 1. But if I were to flip that order, 1 times 2, this is our k, this is our u, so this is 2 to the first, which is 2. So we're asking the question, is this guy going to be a vector space? Take a minute, pause the video, try all 10 axioms, see what you think. Then we'll come back together and discuss it. Alright, so let's look at this funny world where addition is multiplication and multiplication is really exponential. We're asking, is this guy going to be a vector space? So, first axiom that we have to look at is closure under addition. If I take two numbers in this world, let's do some definitions first. U, V, and W are positive real numbers. And C and D are scalars. Remember, scalars can be any real number. So if I take any two real numbers and I add them together, under this definition, it's going to be a multiplication, right? I still get a positive real number. A positive real number times a positive real number is still a positive real number. And we shorthand write that way, R with a little plus where the exponent would be. So yes, this is closed under addition. 2 is our commutative property. So U plus V in this world is U times V. V plus U would be V times U. But remember, now we're talking about properties of real numbers, and the real numbers are commutative. So U plus V does equal V plus U. So we have commutativity under addition. Now let's look at associative property. Does it hold for addition? So we're going to look at both sides. So there's both sides. We want to know, did we get the same thing? Order of operations says we have to do that first. So that's going to be VW. And then if I put these together, remember I'm treating this VW kind of like a unit. So this number plus this number is the product of those numbers. Now let's look at the other way. So u plus v is equal to uv. Treating this guy now as a unit, that number plus this one under this world is UVW. And those are the same. So we have associative property. That holds. Let's look at 4. Let's talk about the 0 vector. So remember what the 0 vector says. It says we're going to take a number, we're going to add something to it, and the goal is to be able to get that number back. Under this world, we're talking about multiplication. So what would our 0 have to be in order to get this number back? Well, we know our 0 would actually have to be 1. So if I take u and I add 1 to it, that in this world is the same thing as u times 1, which is u. So we have a 0 vector, but it's not 0. So that 0 vector is actually the number 1. So that's kind of important because that leads us to that 5th one. So now we're talking about the negative. We're talking about what number can I add so that under this definition, which is really multiplication, right? I get back my 0 vector. Well, my 0 vector is 1. So you have to think about what do those definitions actually mean and what is it saying? Because 0 is not necessarily 0 in every world, and 1's not necessarily 1 in every world. And that's what that axiom is actually trying to say. Let me go back to that first page. There it is. That axiom is really trying to say here and here, what do you have to add to get that number back? And what do you have to add to u to get your additive identity? So remember, additive identities aren't necessarily 0. So this is kind of a cool problem because it's just different. Well, we know that if we're multiplying, then the only way I can get 1 is if I multiply by the reciprocal. Now, does this guy exist in this world? And the answer is yes. We're talking about positive real numbers. So we're talking about positive real numbers. So that definitely lives in this world. This is R plus. Now keep in mind what R plus means. That does not include the number 0. So 0 does not live in this space. So there's our additive inverse. So all of your addition properties hold. Now let's look at our multiplication properties. So I'm going to pick up over here with number 6. Number 6 is about closure under scalar multiplication. So if u is any positive real number and c is any real number, c is a scalar, so this is going to be u to the c. It doesn't matter whether c is positive, negative, or 0. If I take a positive number and I raise it to any exponent, then I'm always going to get a positive number. So that's always going to be in this set. So we are closed under scalar multiplication. 7. Let's look at this guy. we want to know it does C times U plus V equals CU plus CV. So we're going to work both sides out. Order of operations says I have to do that addition first. That addition is really multiplication. Multiplication is really exponential. Rules of exponent says this is the same thing as u to the c times v to the c. So that's what I get. Now let's look at the other side. So cu is u to the c. cv is v to the c. Addition is really multiplication. And we get the same thing. So 7 holds. Now let's look at 8. So now we are treating this sum as a unit. So that's the same thing as u to the c plus d. Remember, multiplication is exponential. Rules of exponent says this is u to the c times u to the d. Now we want to know, is this equal to cu plus du? So let's work it out. Well, cu is u to the c, du is u to the d, and addition is really multiplication. So that checks out. So axiom 8's good. So far, everything seems to be working out. Isn't this kind of cool how we can change those addition and scalar multiplication definitions and have something that completely works out? So let's look at 9. I think this is the coolest thing ever. So we have c times du. Let's work this out, order of operations. Du is u to the d. Then this scalar multiplication would be u to the d to the c. Power to a power means you multiply the powers, and order doesn't matter when we multiply real numbers. Now, is that the same thing as that? That's what the axiom asks. So, we're treating this guy as a unit. So it's going to be u to the scalar. There she is. Same thing. And then 10. 10's looking at a scalar identity. So we need to know, what do we need to multiply by? And remember, multiplication is really exponential to get to get our original number back. What has to be in those blanks? And does this live in that world? So to get u back, we need a 1 here. And we would need a 1 there. Since 1 is our scalar, and scalars can be anything, then that's good. So 1 times our number under this definition gives us that number back. And that is definitely in this world, which is the positive real numbers. So every axiom holds, even though we have really changed what addition and multiplication looks like. Every axiom holds, which means that this guy is definitely a vector space. How cool is that?